There you go. That's the only kind of editing I do on these videos. I'll begin with a word of prayer. So, dear Heavenly Father, we thank you for this day. I thank you again for these students. Just ask you to bless this class, help us to glorify you what we do, and to understand the math together. Lord, in your name I pray, Lord Jesus. Amen. So I went through this proof last time, and so I want to start class here as soon as I can. Oh, that's right. We live in a simpler time down here. A time of switches. Isn't that nice? You can just turn off the light with a light switch. I love light switches. I miss light switches. All right, up on the 4th floor, you know, they're all controlled by the thing. So I want to talk to you guys about limit laws. So I'll just, I could burn a whole lecture just writing this stuff out, but I don't think it would really serve you much. It's probably better for us to just talk about them together, right? So how do you prove the limit as z goes to a of z is equal to a? Well, I'll fix a as a real number. Oh man, son of a gun. That's supposed to be a complex number here. This is supposed to be a complex limit point. All right? Anyway, so let epsilon be greater than 0. You can choose delta equal to epsilon. If we're within delta units of a, well, guess what? F of z minus a is less than epsilon. Therefore, by the definition of limit, you have the limit of f of z is equal to a, which is to say the limit as z goes to a of z is equal to a. This is not surprising, right? So the limit of the variable as you go to the limit point is just a variable. The limit of a constant function is even more silly. I chose delta equal to 42 just to show you that I could. Like, it doesn't matter how close you are. The difference between your function and the constant function is always 0. So of course that's less than epsilon, independent of your choice of delta. So of course the limit of constant is a constant. This one's more interesting. Depending on how you had calculus 1, you may or may not have seen a limit of this before. Dr. Wang, once upon a time, put this proof, I believe, on his first test in calculus 1. And he didn't warn the students it was going to happen. So he's learned since then. If you guys have experienced Dr. Wang, you've experienced a kinder, gentler Wang. See, because well, anyway. To prove that the sum of the limits, the limit of a sum is the sum of the limits, what you do is you assume that both limits are given. Pick epsilon greater than 0. Then you choose a delta for each one that makes the difference between the output and the limiting value less than epsilon over 2. If you do this for both functions, right, then what you do is you pick delta to be the minimum of those deltas, which means you get both of them at once. Then when you look at the difference between the sum of the functions and the sum of the limiting values, you apply the triangle inequality, and because we have both of these being less than epsilon over 2, we get this epsilon over 2 plus epsilon over 2, which is epsilon, and bang. That proves by the definition of limit that the limit of f plus g is the limit of f plus the limit of g. This is exactly the proof that should be given in calculus 1 if you're covering epsilons and deltas in calculus 1. Some of you did not, right? Yeah.
So it's almost like what we had done in the finite intersection of sets when we were proving that the intersection of sets is open.
It is similar in spirit, but there we took the minimum of the deltas. Mm-hmm. Oh yeah, you're right. Yeah, it's the minimum trick again. So if you have control over a finite set of things, like a finite list of things, and you want to have all of those controls in place at once, you take the minimum of all your deltas. That allows you to enforce all of the constraints simultaneously in your analysis. That's the idea. Yeah. Let's see here. So here's the proof that you can pull a constant out of a limit. Basically, you just make your delta equal to, let's see here. Did I ever pick the delta? Oh, yeah, duh. I chose delta such that I get the difference of f of z and L is less than epsilon over the modulus of c, right? Notice that if c is equal to 0, the theorem's true, so that's a separate case. right? So either it's non-zero and I can do this, or it's 0, I can do that. Either way, you can pull a constant out of the limit. Again, if you saw this proof in Calculus 1, this is boring. This is exactly the proof we gave in Calculus 1 with absolute value replaced with modulus. Now, if you didn't see that proof, well, this is scary and new, right? So, and I'm sorry, but it is what it is. But on the other hand, the lion's share of this course is not this kind of, like the proofs that I would ask you on the test are typically proofs that you've already experienced in the homework, all right? Or a proof that I'm going to go through like carefully on the board, yeah? I actually think these are actually reasonable test questions, so it'd be good for you to work through them. They're actually not hard. Let's see here. This one doesn't make a good test question just because there's like so much writing. But the idea of it's very simple, which is that if you can prove pull out a constant, and if you can prove that the limit of a sum is the sum of the limits, then you can extrapolate to an arbitrary finite linear combination by just repeatedly applying the fact that we can pull the constant out and we can break across a sum, right? If we got a sum of 3 things, we can look at that as 2 things added together twice, right? Like the first plus the second 2, and then, well, the second 2 are added, right? So it's like, but I think the proof here I might have by induction. So I said that, this is an inductive claim. I'm claiming it's true for n, right? Obviously it's true for 1. That's the previous proposition. If it's true for n, then if I consider n plus 1 things, then I can look at all of this as one thing, and all of that as another thing. And I already have that. So the limit of the sum is the sum of the limits. That's that proposition. And then by the induction claim, this splits up like so. Oh, we're done. That's n implies n plus 1. So by proof by mathematical induction, we can extend the limit laws to this. Yeah.
Does it work for infinite series?
No. So infinite series require more care, and we'll get back to that when we get back to it. So, convergence requires finesse. Now, the limit of a product is the product of limits. I doubt you proved this in Calculus 1. If I prove this in Calculus 1, it's because I've got a really good class or I'm just an idiot. Or maybe both, I don't know. But this is not easy to prove, I don't think. And the proof, basically you're trying to make the difference of the product smaller than epsilon given control over the inputs, right? So if you look at this difference, you can add zeros strategically like this and rewrite it like so. All right? Then, yeah, the triangle inequality, plus the fact that the modulus of a product is the product of the moduli, and I factored out the g of z, and I factored out the L sub f over here. Now this I can make as small as I want. That I can make as small as I want if I control the input z. LF is just a number. And this over here, though, well, good news is that I can bound that. If the limit of g exists near the point, I can make this, I can't make it small, but I can make it close to something, all right? Anyway, so of course g of z goes to L sub g, I should say. In the limit, that goes to L sub g. So you play this game, you have to pick 3 deltas, like this. This is not my proof, guys, either. This is a proof I found on a Wikipedia, a wiki article somewhere. All right, I used to have a proof in my Calc 1 notes that involved like solving a quadratic equation. It was really quite ugly. This is much prettier. So you pick delta 1 that gets you the difference between f of z and your limit point less than that. You pick a delta 2 that gets you that close to the difference between g of z and its limiting value, right? And then you bound the difference between g and its limiting value by 1. So if you play these 3 games all at once, you pick delta 1, delta 2, delta 3, and we can do that because we're given that the limits exist, all right? And you put that all together with the triangle inequality I showed you before, well then, it all comes together, all right? Because the g of z, you can also play this game, right? Add 0, triangle inequality. We're assuming this is less than 1, so we get 1 plus modulus of the limit for g. So then if we pick delta to be the minimum of all 3, we want to have our cake and our pie and our donuts and eat them too, right? And I might be hungry. Anyway, so we get, again, the estimate, and then put it all together, we get epsilon. So this is the proof that the product of the limit of a product is the product of limits. This is not an easy thing to prove, I think, right? But this is a standard proof for this, and this holds in the real domain just the same. Limit of the power function, well, if you've got the limit of z as z approaches a as a, right? And you define z to the n as z times z to the n minus 1, right? Where n is an integer. We're not in that complex power business that you just suffered through in your homework, right? N is an integer, a positive integer. Then we can just, actually use induction. If we assume it's true for n, look at n plus 1. By definition, it's that. But by the product of the limits theorem, we have the limit of that times the limit of that. But by induction, that's a to the n. And by my first thing I showed you today, that's a. So we get a to the n plus 1, which is what we were trying to prove. There's the induction claim for n plus 1. So we can prove the limit of z to the n is a to the n by induction. And then if you've got that, well, then you can get the limit of, as a goes to, z goes to a of a polynomial is just p of a, right? Because you can just apply the previous thing I said plus the, pull the constants out and break across a finite sum, and voila, you can just plug in an a into a polynomial if you've got a limit of a polynomial. Yeah?
So, sorry, if we go up to the exponential one.
Uh-huh.
So, n is a member of n.
N is a net.
Right.
Yeah.
How do we extend that to the real numbers, and then how do we extend that again to the complexes?
I wouldn't. I'm talking about natural numbers here. I'm not trying to do anything else. So, yeah.
Well, I know, but I mean... We
can do that another day. We're not going to do that right now.
Oh.
So, you can talk to me about that after class, but that's like, I can't do that, actually. That's an interesting question, but in order to do that, I have to pick a branch of the complex power function, and I can only do that on a split complex plane. In fact, the complex power function is not continuous. If you try to go to the whole complex plane, it necessarily has an angle jump. Worse yet, it has infinitely many values, so we can't even talk about it as a limit of a function because it's not a function. So if I was dealing with like z to the, if n was a complex number, I can't do this until I make a choice of a branch cut for the complex power, and then I can talk about it, but without that, yeah. But this is easier than that, right? We're just talking about functions, integer powers, yeah.
By a branch cut, you mean like -5 pi?
I mean something I was trying not to talk about right now. So, but I mean a choice of angle. So you're removing a ray from the complex plane where the angle jumps. That's what you need to do in order to have a continuous assignment of angle in the complex plane with 0 removed. And the complex power function and other things have been built using argument, right? Which is, anyway, yeah.
Are there things in real variable calculus that don't translate to complex variable calculus?
Yes, in fact there are, thank you. That was my next point. So, listen, what does this theorem say in words? This says that a complex polynomial, it says every complex polynomial is continuous. Where? Where is it continuous?
Every.
On the whole complex plane. Polynomials are nice. All right? And so actually, if you want me to summarize what, and here's the limit of a composite is the composite of the limits. I'm not going to, you can read it. This one right here, though, the limit of the reciprocal function, here is where I could not just use the real proof, because my real proof is based on the ordering of the real numbers when I was looking at it. And so that proof falls apart here. I had to go back and use the theorem that you guys are proving the second half of in the homework to take the function and look at its real and imaginary parts separately to evaluate the limit. At least that was my approach. There's probably some kind of slick inequality based with just staying at the level of the modulus, but you see I get stuck on that stuff last time, right? So I have to do something that's less clever, which is just to bust out the real and imaginary parts. So like reciprocal function is this, right? That's the conjugate over the conjugate times the variable, right? This is the z bar over zz bar formula in detail. And so my real component functions is that. My imaginary component function is that. And so if I take the limit as z goes to z naught, it's pretty clear from like the theory of limits in Calculus 3, right? And what is that? If we had to summarize that theory, what did it say? It said, if you're approaching a limit point, right? And you can plug the limit point into the formula and nothing bad happens, that's the value. On the other hand, if there's 0 over 0, or if you've got, 0 times infinity, well then further analysis is required, right? Just like Calculus 1. If you can just plug the limiting value into the expression, game over, that's it, that's the limit. I mean, we make all these limit laws and fuss and fume over it, but that's it at the end of the day, right? Most limits are actually pretty trivial to calculate. We just plug it in and it's done, yeah? However, the 0 over 0 limits are actually interesting, right? Because every derivative is a 0 over 0 limit. Because you're calculating what? The rate of change of the output over the input as they're both going to 0, right? Every limit, every difference quotient that you're calculating a derivative is an indeterminate type. So the indeterminate type is not just, of no interest. It's actually of primary interest. And yet, most functions are mostly continuous, right? So usually we can just plug in things like this. I don't get into trouble. Why? Why don't I get into trouble?
You can't have 0 in the denominator.
Right, I can't. And the only way to have 0 in the denominator is to have both x not and y not both 0, right? And that's not happening because we assumed, I hope we assumed, a not equal to 0. Okay, good. Whew. All right. And so there, now I'm going back to the theorem that you guys proved the other half of in your mission 2, all right? That I can, the limit of a complex function is the, the linear combination of the limit of the real part and the limit of the imaginary part, which is that. So, yeah. So there's something I couldn't just use the complex, I couldn't just directly steal my real proof from. Now that's not really the answer to your question, though. You're asking something deeper, which is what is the difference between real calculus and complex calculus, right? And that's a question that we'll be answering the whole course. So we're not going to finish answering that today for sure. Yeah. The limit of a quotient is the quotient of the limits. The proof is pretty much the usual one. What else can I tell you? Oh, and that brings us to chapter 4. All right, so let me put this away now. We're going to write things out. So I do want you guys to know the definition of limit, like the epsilon delta definition of limit is something you need to learn. If you don't know it yet, you should try to memorize that. It would be a healthy thing for you to try to pick 1 or 2 of those things we just went through and prove them for yourself. And I don't mean the ugliest one. I'm not talking about the product one. If you want to learn that one, well, more power to you. But I'm thinking more like the limit of the sum is the sum of the limits. That's a good test question. The one with the epsilon over 2's in it, that's a good question. Or just pick something simple for yourself, like try to prove the limit of z squared as z goes to a is equal to a squared from using epsilons and deltas, like not using the limit laws, right? I think I put something in your mission 2 like this anyway, so that'll take care of itself, right? But it's not the primary interest of this course. Now, so turning gears here, we're now in chapter 4. And I think you guys will like this. This is the theory of differentiation. On Euclidean space. Now, I'm mostly focused on the plane. But what I describe here briefly is how do we differentiate a mapping from, say, Rn to Rm. So I'm going to be just a little bit more general than I need to be here, and then we will soon transition back to just putting n and m both equal to 2, because we're studying maps from the complex plane to the complex plane, which really means we're studying maps from R2 to R2, all right? But it's just as much trouble to give you a definition for differentiation yeah, we're good. We'll give you a definition for differentiation of maps from Rn to Rm, so why don't we do it? Here it is. If f is a mapping, let's say from U, which is a subset of Rn to Rm, is a function, which you could say, or if you want to, you could call that a map. Map and function are kind of synonymous in this regard. Some people take function to necessarily be real valued. I'm not like that. Okay? So if this is a function and A is an element of U for which the limit below exists, then we say f is differentiable at A with derivative df sub A, let's say. And df sub A is itself a mapping from Rn to Rm. All right. Now, which limit am I talking about? I'm talking about the following limit. The limit as h goes to 0 of f of A plus h minus f of A, all right, minus dfa acting on h. Now, let me dial it back a second here. Let me, instead of saying dfa, let me just call this L sub A, just L. We just call that L. For the sake, that'll help us with proofs today, because we don't want to have to suffer through this notation every time we're thinking about this concept, all right? But L here is equal to the derivative. Well, I should say really L is the differential at A. Differential of f at A, to be more precise. And close parenthesis here, all right? And it's equal to 0, all equal to 0. And so we have to divide by something. Now, if it was going to be just like calculus 1, we'd just divide by h, right? But why can't we do that? In this context, what kind of limit is this? It's the kind of limit that I just described the two-dimensional case of in the last chapter, right? So first of all, if you really wanted to be fussy, you're like, hey, hold on a second. You didn't develop the theory of n-dimensional limits in my notes. That's right. I'm trying to be not too abstract here. So technically speaking, these kind of limits, you'd have to, talk about topology in Rn. It's really the same as what we talked about in the plane. It's almost identical. You just replace like distance in 2 dimensions with distance in n dimensions, but it's practically the same discussion. So the definition of this limit is again given with epsilons and deltas, just in Rn rather than R2. All right, so that's that. I can't divide by h. H is a vector. Now, if we're in the complex plane, then we can divide by h, as long as h is not 0, right? So that's one thing that the real calculus doesn't have as nicely as the complex calculus. That's sort of another answer to your question. We'll find many answers to your question. But this is just the length of the vector. This altogether is the so-called Fréchet quotient. And to be more precise, if a function has, and this L by assumption is a linear map. L is linear. That's assumed here in the definition. Linear transformation. If you know what that is, great. Many of you do, because you've either had linear or you've, yeah.
h in the limit, then is that also length of the h approaching 0?
Nope. This is the multi-dimensional limit, h going to 0. This is the limit which approaches 0 from all possible directions in n dimensions. It's the multivariate limit. Limit as the length of h goes to 0 would assume a symmetric approaching to 0. And we make no such assumption that we're symmetrically approaching 0. That would be a different concept. But that is it. That's the derivative. And what it really says in a nutshell is just this, is that if you want to, here's the long and short of it, f of a plus h is approximately equal to f of a plus L of h. So this is like the best linear approximation to f near a. That's what this quotient's capturing. All right? Now, oh man. So, yep.
So the domain of the derivative can be expanded beyond that of the original function?
Yeah.
Okay.
But this is at a point. So what you're thinking about would be the assignment of the derivative function. No such thing exists. The derivative as a function would have to be this. It's the assignment of the differential a assigns to df of a. The input's a point in Rn. The output is a linear transformation from Rn to Rm. That can't usually be thought of as a function. So it's so much worse than that. And this is part of the reason we don't talk about this notion of differentiation in Calculus 3. Calculus 3, you talk about derivatives of space curves. You talk about derivatives of functions of several variables. You talk about derivatives of vector fields. But you never actually talked about the derivative of a function from like R3 to R2. Or what's the derivative of a function from R4 to R7? Like, you haven't done that in Calculus 3. This will subsume all of the derivatives that you've done in Calculus 3. They're all special cases of this general notion. All right? But the one thing we can come back to, though, is the partial derivative. Like, partial derivative of f with respect to the jth variable at a, what would that be equal to? So was there a question, or? Hold on to it. We'll probably answer your question. So here, this is a genuine real limit as t goes to 0 of f of a plus tej minus f of a over t. So the partial, and I'm again dealing with a function from Rn to Rm just for the sake of being abstract for a second. So we can define the partial derivative of that function. The obvious question is, so how does the function and the partial derivative, how does the differential and the partial derivatives relate? Because partial derivatives, that's your happy place, right? We can calculate partial derivatives all day long. Everybody's happy in here, right? Be like, please, more of that. This, of course, is nothing more than the derivative holding, all of the variables fixed except for the jth one, right? You're just varying the jth variable is what that is. If you guys don't know, I'm sorry, I'm using notation you may not have known. Ej is zeros, 1. So this is in the jth spot. So it's like E sub j is the analog of like I, j, k in the multivariable calculus. Like E1 would be I, E2 would be j, E3 would be k, or if you've taken my calculus, x hat, y hat, z hat.
Or like columns on the identity matrix.
Yes, they are the columns. Exactly. The identity matrix we could write as E1, E2, En if we're talking about the n by n identity matrix. Good point, yes. You question, comment?
I don't understand the pattern for EJ.
It's just the jth one.
Oh, E is just like the sum.
Here, let me remove the ambiguity. You calculate the jth factor, calculate the ith component, Kronecker delta ij. This is 1 if I is equal to j, 0 if I is not equal to j. This is how we should talk about things. It's a better way.
So there's one different E,
Just one.
and everything else is 0.
Correct. This is the so-called standard basis. If you guys are currently in the midst of 221, these are important. Like, you can do all kinds of stuff with the standard basis. Anyway, an example. Here, how about this? F of st equal to s squared plus t cubed, 2st, s plus 3t. So here, my f is a mapping from where? From R2, right, to where? To R3, actually, right? By the way, I write this to mean column vector for what it's worth. That's really not going to be much of an issue in here since we're pretty much just doing 2 dimensions to 2 dimensions. But anyway, so partial f, partial s actually for me would be 2s, 2t, 1, and partial f, partial t here would be 3t squared, 2s, and 3. So I'm actually using a theorem, which is that this partial derivative, the partial derivative of a vector valued map, is actually just the vector of the partial derivatives of the component functions, right? Basically, well, anyway, listen, if you want me to get into more detail about this, come take advanced calculus with me. I will divide these things and do them carefully there. But here, let's just kind of go on. What happens then is you can put these two things together into what's called the Jacobian matrix for f. Jacobian matrix for f, the first component, the first column is partial f, partial x here. Excuse me, s. My variable was s, right? So partial f, partial s, and then partial f, partial t. This is the so-called Jacobian matrix of this map, all right? And what this thing is actually the standard matrix of the differential. And I'm doing it at an arbitrary point, st, right? You could plug in a point, you know. But it's actually, you know, 2s, 2t, 1, 3t squared, 2s, 3. So the derivative actually we should think of essentially as a matrix in general. Let me give you a definition here. You're okay. Well, so I should stay on my notes, otherwise I'm going to get into trouble. I've already, oh man, I had a plan. If I could just follow my plan and not be an idiot. Rats. Well, I have ruined a perfectly good lecture. Yes?
So, I don't know, this might be a little bit redundant.
Uh-huh.
So are we doing this because R2 is isomorphic to the complex plane?
We're doing this because I need to prove a theorem of real calculus, which is the bedrock for a fundamental theorem in this course about complex analysis.
Okay.
But it is genuinely a statement about real analysis, not a complex thing.
Okay.
So that's my goal today, is just to explain to you what continuous differentiability is and why we need it. But I need to explain to you what real differentiability is so you can appreciate what we're up against.
Okay.
So we're working on it. At the moment, I'm trying to show you how it relates to partial derivatives. So in short, we can build this differential. Let me just get to it. The Jacobian of f is partial f, partial x1, partial f, partial x2, partial f, partial xn. You can build it like that. Or you can think about this as a stack of gradients of component functions. All right, and in my language, those are transposes because I have to make the column vector into a row vector. So just for the sake of my, you know, what do you want to say? Math OCD? What do you want to call that? What's the word? Pedantic. It's my pedantic nature. So anyway, f is again, I'm thinking f is a mapping from Rn to Rm. So that means that you can break up f into m component functions. In my example 1, there were 3 component functions. See the component functions? This one, this one, this one. Those are the 3 component functions. And to find the first column, you just differentiate the component functions with respect to the first variable and put them in a list and so forth. Now, the gradient, what's the gradient? You guys know that already, right? What's the gradient in n dimensions? Remember the gradient? In 2 dimensions, it's like partial f partial x comma partial f partial y. Same thing here, just goes on and on. See how that works? First derivative, second derivative, derivative with respect to first variable, derivative with respect to second variable, derivative with respect to nth variable. So as you think about those, they fill out the gradient vector. Each row is a gradient vector. Okay. And then here's the connection with my, you know, Fauché derivative is simply this. So here's a theorem. If the function, right? If the function is differentiable at a, okay, then the partial derivatives exist at a, and you can build the formula for the differential as follows. dfa of h, it's simply equal to the Jacobian matrix of f at a times h. And this is a matrix column product. Again, the theorem that I'm, you know, claiming here is that if f differentiable at a, then we have this formula. So before I continue with my madcap tour of real differential calculus, let's take a break from this wild world of new abstract calculus, which is really not, it's really not that bad, honestly, folks. Like but you know, to do this justice, it takes me about like 3 weeks, well, not 3 weeks, about a week in advanced calculus. All right, but really, it's best if you've already had what? If you already had linear algebra, right? Like my advanced calculus, you should have had linear algebra before you take this course with me, ideally. I don't have it as a prerequisite, unfortunately, but like no one who's not had linear algebra has ever stuck around in my advanced calculus more than about a week. So, yeah. But what I want to show you here now is let's look at these notions of partial differentiation for complex functions. I want I want to look at these derivatives for complex functions with some formulas that we've looked at already. Let's just see how it goes. Yeah? So this is where if I'd just been following my notes, we would have, found a slightly more peaceful path through this material. So here, if the thing I just covered up, right? Partial derivative, we can take the partial derivative of a complex valued function, right? What are we doing when we do that? We're taking the derivative of an R2 valued map, right? A function on the complex numbers is a mapping from R2 to R2. So the definition for partial differentiation I just wrote down applies here. And it's also totally unsurprising. Like, man. Oh, my laser. All right, I will take a breath. F of z, come on. Well, man. So f of z, we can think of as a mapping from R2 to R2. What would this look like without the complex notation? Here's what it would have looked like outside of the world of complex variables. That would look like f of x comma y, right, equals to e to the x cosine y, comma, e to the x sine y, right? That's what we're looking at. But when we use the complex notation, we can simply write what? F of z, oh thanks, f of z equal to, I'll get it eventually here, f of z equal to e to the z, right? Like, man. So what do you think the complex derivative of e to the z should be? No one has a conjecture. If we haven't defined complex derivative, right? We'll do that next Tuesday. Yeah, e to the z. That seems like a very good suggestion. So something interesting happens here. Right? When we calculate the partial derivative of f with respect to x, we do what? The x derivative of the real part, the x derivative of the imaginary part. So you know how to do that. I mean, it's kind of boring. It seems like nothing happens, right? And so, lo and behold, partial f partial x is e to the z. That's kind of funny. Wonder what that means. How about partial f partial y? Well, there I get a minus from the cosine, and that differentiates to sine. Cosine, sine differentiates to cosine. I can't use my words today. And if you tilt your head and squint, you can see that I can factor an I out of this. Notice that this minus becomes an I squared. So this is exactly I e to the z. Let me write that down. The Jacobian for f, well, the Jacobian for, let's say, little f, my notation, apparently is e to the z and then I e to the z. That's what we just saw. That's an interesting pattern, I think. How about z squared? The partial derivative of z, so z squared, come on. The component functions for z squared are x squared minus y squared and 2xy. So partial differentiation with respect, it gives me 2x plus I times 2y. Hold on a second, 2z. Huh. What do you want the complex derivative of z squared to be? I want it to be 2z. Isn't it interesting that the partial derivative of f with respect to x here gives me what I want the complex derivative to be? Why is that? Something we should think about. On the other hand, if I partial differentiate with respect to y, I get this. And if you tilt your head and squint, you can factor out an I, you got 2iz. So it looks like if we have, you know, the Jacobian for g, where g of z equals to z squared, well, apparently it's just z squared excuse me, z squared, listen to me. It's 2z, 2iz. That same pattern again, isn't it? That same pattern again. So does this pattern, oh, you got it, okay, cool. Does this pattern hold always? Well, if I'm asking the question, the answer must be no, right? Right? So here's a theorem that we'll use over and over and over again, right? And this is a pretty easy one to prove. If you're looking at functions from complex to complex and they have partial derivatives, and of course we're talking about real partial derivatives, the only kind we know about, then the partial derivative of the sum is, you know, the sum of the partial derivatives. And that's true for the x variable, it's true for the y variable. This is what's more interesting though. The partial derivative of a product has the product rule. This is not immediately obvious because the product we're talking about here is not a real product, it's a complex product. So there is something to prove here. The proof is not hard though. If we write f is equal to u plus iv and we write g is equal to a plus ib, when I multiply this out, I get ua minus vb is plus I times this sum here, right? So how do we partial differentiate f times g? Well, we partial differentiate that and we partial differentiate that, right? So when I hit it with the x derivative, I've got 1, 2, 3, 4 products to differentiate. So I apply the product rule 4 times. I get 8 terms, like so. And then I group things and it's that. It's literally just the definition of the complex product and the product rule with our definition of partial differentiation. So it's, but there it is. Now we know it, so we can use it, right? So here's another example. I decided to differentiate sine z. See how this goes. So sine z is sine of x plus iy, right? And the usual calculation, I use adding angles formulas, which we still have not justified, but don't worry, I will put it in the future homework. You will get to it. But we'll eventually prove this identity. It's not hard. And then I change my cosine to cosh, and I change my sine to I times sinh. There's my real and imaginary parts of sine. Cosine has these real and imaginary parts. So, and I thought, well, for giggles, I'll look at sine of z squared. So sine of z squared, since z squared is this, I have to replace the real part with x squared minus y squared and the imaginary part with 2xy in my formula up above, and that gave me this. Right? I traded my y for 2xy, I traded my x for x squared minus y squared. So there's sine of z squared. And then I said, well, I'm a glutton for punishment. Let's calculate the partial derivative of this with respect to x. So I did it. And guess what happened? After some calculation, I found that what I calculate is actually, lo and behold, shock and awe. I mean, there's really no awe. Maybe there's no shock. Maybe there's some awe. Maybe like awe. Not even that. I'm not sure what there is, but it's not too surprising, is it, that the partial derivative with respect to x of sine z squared is 2z cosine z squared. At least I want the complex derivative of this. Seems like it should be that, right? If there's any justice. And we've started to notice a pattern that the x partial derivative seems to match what we want the complex derivative to be. It's an interesting pattern. Now, at the moment, this is all just formal nonsense, right? Because we have not defined the complex derivative. We'll do that next week. Now, this example, I intend to show you that it doesn't always work out so nice. Like, generally speaking, if you've got the composite of two functions like this, f composed with g, come on. F composed with g, when you calculate the partial derivative with respect to x, you get this. And so generally speaking, there's some terms that we haven't been picking up on in the previous. So like here, this one, if I look at the modulus of z squared, and I look at g of z as just the z squared function, then f of g of z is actually this. And so if I calculate the x derivative, I get that. But on the other hand, if I calculate partial f partial x g of z times partial x partial g partial x, I get that. Which is to say that I'm not getting what I was kind of expecting from the previous pattern here. But anyway, let me not try to, this you need to read. It's not going to work for lecture. All right. So my point to you is that for a complex function, the Jacobian matrix is just a 2 by 2 matrix, right? And it's the partial derivative. The first column is the partial derivative with respect to x. The second column is the partial derivative with respect to y. And that's it. We have noticed for some formulas of the complex domain, there's some kind of pattern, right? The pattern was the first column and the second column are related. The second column was obtained by I times the first column for like the derivative of sine and the derivative of z squared. We've seen that pattern both times. So we'll come back to that next week, why that is, all right? Now I have to answer a more technical question. The more technical question is this. If the partial derivatives exist, does that imply that the function is differentiable? In other words, what's the converse to this theorem? And I need to show you some cautionary examples on what happens to us when we try that. So, I'll get to it. Oh, by the way, here's more Jacobian examples. I have some of them. Like, by the way, maybe this is, probably some of you are wondering, how does this stuff fit in with Calculus 3? Calculus 3, space curve, Jacobian matrix for space curve, velocity vector. On the other hand, if you're looking at a function from 2 variables to 1 variable, the Jacobian matrix is just the gradient. So it reproduces both the velocity vector and the gradient concept, and more. All right, anyway. You might also wonder, how does this connect with Calculus 1? How do you get from this Frechet differentiation to like the difference quotient concept of differentiation? This subsection right here, I explain in detail how to go from one to the other and vice versa. They're equivalent concepts in the context of one dimension. All right? But that, that's really not this course. That's advanced calculus. But I've included that there for your reading if you want. So continuous differentiability is what we need to understand that we need. And so to understand what continuous differentiability is, you must first understand what it's not. So you need to see an example of a function. And this function, f of x is equal to x over 2 plus x squared times sine of 1 over x, given the definition f of x is 0. You can prove that the derivative of this function at 0 exists. Right, in the sense of like the limit, the difference quotient definition of calculus 1 derivative. So the derivative at 0 exists. In fact, the derivative at 0 exists, and yet when you calculate the derivative away from 0, what do you get? You get this, yeah. And what's the deal with this formula? What happens? I mean, as x goes to 0, this is okay. That's getting small. But what about this guy? What happens as x goes to 0 there? That goes to, well, it goes to 1, it goes to minus 1, it goes to a half, it goes to a quarter, it goes to every single stupid value between minus 1 and 1. It oscillates like mad as x approaches 0. So the graph here, what I'm looking at, the function is the red one. So the function just kind of And then it gets in here and it just kind of wiggly, 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 and it comes back out, right? But it's going to 0. And it's going to 0 tamely enough that it does have a tangent line, technically, depending on your definition, at 0, and its slope is a half. And yet that tangent line does not well approximate the function, because this function is not increasing at rate a half on any reasonable interval of 0. It's increasing and decreasing infinitely many times as you approach 0, because the derivative is discontinuous. So this is a function which is differentiable at 0, but not continuously differentiable at 0, because the derivative is not continuous. So the derivative not being continuous is evil. You can find quotes from 19th century mathematicians. This is the sort of thing that gave them nightmares. Like, there are literal quotes from people. But so then you're like, well, okay, fine, but surely if all the partial derivatives exist, then the tangent plane must make sense, right? Well, let's look at that. Here's a function that has tangent partial derivatives which exist. They exist, all right? And yet the tangent plane at 0 does not exist. And why is that? Well, so like along the basically what happens is you've got this, like, you can't fit a tangent plane here, despite the fact that the function is pretty well behaved along the coordinate directions, right? Yeah? So it's not enough for the partial derivatives to exist at a point. That doesn't give us differentiability. Now, if by the way, I keep talking about tangent plane. If you think about this, the linearization, the graph of the linearization, if you will, is the tangent plane, if you'll allow me that sleight of hand there. So whether or not we can see a tangent plane is tantamount to whether or not we can find a differential to satisfy the Frechet quotient. That's the way to think about it. We can't do that here. It's not differentiable at the origin, even though the partial derivatives exist. You're like, well, that's just a quirk of the coordinate directions. Maybe if the partial derivatives exist in all directions, then surely we must get differentiability, right? Wrong. This example is one for which the partial derivatives in all possible directions exist and are 0 at the origin, and yet it is not differentiable because of this annoying blue hair that's sticking out. I say that this function is continuous at the origin. I don't know if I believe that. That might be wrong. I'm not sure about that. In the notes I say that this is continuous and all of the partial derivatives exist. And I say partial derivatives in the generalized sense of directional derivative. Remember Calc 3 we talked about directional derivative? So a directional derivative is a partial derivative in some other direction other than the coordinate axes. That's what I meant by all partial derivatives exist. All right, anyway. So that's a problem. That's why we care about this. Continuously differentiable. A continuously differentiable function is one for which all the partial derivative mappings exist on an open set containing A and are continuous at A. That will kill the examples I just showed you. All right. So, and it turns out this is the secret sauce. If you have continuous differentiability of your functions, then I can take the partial derivatives and I can construct the differential. In other words, continuous differentiability implies differentiability. All right? But the nice thing about continuous differentiability is it's just about partial derivatives. All right? So, and I prove this over here. This is a proof in n dimensions. I'd like to give you a proof in 2 dimensions, yeah? Because we're 2-dimensional here, aren't we? So let me give you the 2-dimensional proof, and Hopefully I can do it.